Good morning. This is our 24th lecture of the course Compressible Flow and Gas Dynamics. In the previous lecture we discussed about the area velocity relation and we have obtained the equation dA by A equal to m square minus 1 dV by V. Okay, so this was the equation which we obtained between area and velocity, and in this particular equation basically we had assumption of quasi one dimensional flow. Okay, so now if you see, we found from this equation that if I have say a converging section and say one diverging section, and if my Mach number is less than 1, then as per this equation, for Mach number less than 1, if my area is decreasing, then velocity should increase. So this will be direction of nothing but increasing V. Okay, and in case of same situation, say Mach number is, so for this entire situation Mach number is less than 1. So if I have increasing area, then as per this equation I will be having nothing but decrease in the velocity along the increased area direction. Okay, then we also saw that if we have supersonic flow situation, that is our Mach number over here is greater than 1. So if our Mach number is greater than 1, then what was happening, as my area is decreasing, so velocity also decreases along with decrease in area. Okay, and here velocity will be increasing along with increase in area for a supersonic flow situation. Okay, so this is something which we have actually done in the previous lecture. Now by taking the advantage of these concepts, we can have one very important device which is called as convergent divergent nozzle. Okay, so here you can see that you will be having one convergent section first, then you will be having some section of fixed area which is having the minimum area, and then you will be having a divergent section. Okay, now in this situation, if we consider that if my initial flow Mach number is less than 1, okay, so it means initially I have nothing but a subsonic flow situation. Okay, so what will be happening over here, this area velocity will keep on increasing, and we have seen from the previous equation only in our previous lecture that we get minimum area situation. So over here minimum area is actually this particular section. This section is called as throat. Okay, so at the minimum area our Mach number will be nothing but equal to 1. So at this point I will be having Mach number equal to 1, which makes a sonic condition over here, and once I have this sonic situation, then if I have increasing area, so here I will be having further acceleration in the flow, and here I will be having actually Mach number greater than 1, which is resulting in supersonic flow situation. Okay, so in a single convergent divergent nozzle, if I start with the subsonic flow situation, I can actually reach to a supersonic situation, and also because the relation which we have derived, dA by A equal to m square minus 1 into dV by dV, this is we have derived by considering the assumption of isentropic flow. Okay, so over here I can say this process is nothing but the isentropic expansion of the flow. Okay, so in this convergent divergent nozzle, what we are achieving is we are changing our situation from subsonic to supersonic situation. This is nothing but the isentropic expansion of the flow. Now I can utilize this similar variation in the area. I can utilize this similar variation in the area even to compress, even to achieve the isentropic compression. Okay, so how we can do that? So if I consider that my initial Mach number is greater than 1, so I have nothing but a supersonic flow situation. Okay, so what will be happening over here in this, when I will be moving in the downstream direction, my Mach number will keep on decreasing with decrease in area. Okay, and once again at the minimum area I will be getting Mach number equal to 1, which is a sonic situation, and after this sonic situation, as my area is increasing, so here I can actually have subsonic situation with decrease of Mach number. So here I will be having subsonic situation. Okay, so this type of device is actually, now you can see that we have the same device, we are not making any changes, we are having the convergent divergent section only, but what we are basically doing, we are doing the isentropic compression. Okay, so ultimately what is happening, velocity of the flow is decreasing over here, so that will ultimately reflect in terms of increase in the pressure at the exit. Okay, so that's why I can call that in the same device, if I control the flow parameters, then by just controlling the flow parameters I can even achieve the isentropic compression process. Okay, now if you typically see, if you see the practical applications of this type of cross section, so you can see in case of a rocket engine, so what happens in case of a rocket engine, if you see in case of a rocket engine, we will be having a combustor. So say this is my combustion chamber. Okay, this is my combustion chamber. So in this combustion chamber, actually one inlet I will be having for the fuel and one inlet I will be having for the air. Okay, and say, so this is my air is entering over here, here say my fuel is entering. Okay, now what will be happening, this air fuel mixture will create the high pressure and high temperature gases over here. Now the major function of the rocket engine is to create the thrust, and in order to create the thrust, we know that from our thrust equation, that thrust is having major contribution from change in momentum across the inlet and outlet. Okay, so if I have to increase this change in momentum, what I have to do, I have to increase the velocity at the exit. Okay, so to increase the velocity at the exit, what I will be having, I will be having my section something like this. So this is a convergent divergent section. So this, you can see some bell shaped nozzle over here. Okay, so this is the typical design of a rocket engine. So in case of a rocket engine also, we take the help of this convergent divergent section in order to create the situation of supersonic flow. We want to basically increase this exit Mach number. So here I want to have Mach number very larger than 1. Okay, so here it will be less than 1, and at this section it will be equal to 1. Okay, so this is, you can see typically one say rocket engine or even your aircraft engines, where you have to also create the thrust force. So these are nothing but the examples or applications where convergent divergent nozzles are actually used significantly. Okay, then similar way, say if you want to develop one supersonic wind tunnel. Okay, so then what will be happening, so say if you want to test some prototypes of different aerodynamic components in a wind tunnel at the supersonic conditions. Okay, so what we have to do, our focus will be to create the supersonic wind tunnel. So for creating the supersonic wind tunnel, what I can do, I can consider the section of the wind tunnel something like this. Then I can have some converging section. Okay, then I can have some diverging section over here. Then I will be having my fixed test section, and after the test section, once again I will have convergent divergent section. Okay, so what ultimately will be happening, let me tell you. So say I can assume that in front of this section I have nothing but my reservoir. So here I have a reservoir of air. Okay, so ultimately atmosphere I can consider as nothing but the reservoir for air, and at the atmosphere our air will be having almost zero velocity. So corresponding to this, whatever the pressure and temperature I will be having, I can call these as stagnant pressure and stagnant temperature. Fine, P naught and T naught, and so my Mach number will also be very low. Now if I use some mechanism to pull the air into this section. So here ultimately I will be having, say, Mach number less than 1. Okay. Then this Mach number less than 1 actually enters into the convergent section. So in this convergent section, its velocity will keep on increasing, and we will consider this convergent section in such a way so that at this minimum area point I have nothing but Mach number equal to 1, and after that I will be having divergent section where my Mach number will become greater than 1. Okay, so here I will be having supersonic flow situation. So this section from this point to this point over here is nothing but a nozzle. So this is my nozzle over here. So this nozzle is sometimes also referred to as D levels nozzle, or even simply levels nozzle. So the name is given to this device D levels nozzle because he was the scientist who have used for the first time this type of convergent divergent section for increasing the efficiency of a steam turbine. Okay, so that is the reason that sometimes this in his name also we call this as a nozzle. Okay, now in this nozzle, so this section is nozzle. At this point I have got the supersonic flow situation. So now once I have this supersonic flow, then this will be my constant area section over here. So this is the actual portion where I can actually place my aerodynamic object, and then I can do the testing. Because what I want to do, I want to test the aerodynamic object under the supersonic flow situation. So at this point my velocity has become supersonic. So after this I don't want to make any changes into the flow situation, okay, because I achieved the desired flow conditions. So then in a constant area section actually I can place my aerodynamic objects and I can do the testing. So this will be my test section over here. Is this point clear? Now if at this point my velocity is very high, if I do exhaust of the flow or fluid, say this is my fluid which is flowing, if I do exhaust of the fluid to atmosphere at very high velocity, can you tell me what will happen? Across, if I take my, say, wind tunnel only up to this point, so what will be happening? Here flow velocity will be very high. So when very high flow velocity will go outside, so across this complete device, change of momentum will be very large, and it will be creating a large amount of thrust force in the leftward direction. So to hold this structure, in order to provide the structural rigidity, I have to provide very large amount of force in the opposite direction. Okay, so to avoid this issue, so that we should not have any structural damage to the system, we don't want any thrust force in this situation. So what we do to do so, we will be using one more section over here. Now in this section, if you say your Mach number is greater than 1, because here situation was supersonic flow, and after this I have a Mach number of 1, and then I will be having Mach number less than 1, and this section we will be selecting in such a way so that the exit velocity is very small, almost approaching to 0. So this is how we will actually design this nozzle. So I can say that this exit section is nothing but acting as a diffuser over here, because it is decreasing the velocity and increasing the, say, pressure. Okay, so this is acting as a diffuser over here. So this is you can see the schematic representation of a wind tunnel, which we can use for the testing of the different aerodynamic objects for supersonic flow situations. Okay, so this is another important application where I can see actually the application of convergent divergent section. Now let's try to see specifically our nozzles only in more detail. Okay, so different aspects of the nozzle in more detail, let's try to understand. Okay, so typically if we see in case of nozzle, as I earlier also told you that due to the changes in area, flow will be either two-dimensional or three-dimensional. Okay, but we take the assumption of a quasi one-dimensional flow. Okay, so by taking this assumption, we have actually derived this area velocity relation, and another important point is this area velocity relation also further we have derived by taking the assumption of isentropic flow situation. So we are idealizing it to more closer thing. Then this relation for isentropic flow situation is now applicable for almost all type of fluids, but if we use it for a real fluid, then we will not be able to find the closed form solution. Okay, so closed form solution for a nozzle flow is applicable for specific situation of calorically perfect gas or perfect gas only. Okay, so if we do not consider the perfect gas, then we will not be able to find the analytical solution and we have to go for the numerical solution. Okay, so whatever analysis I will be presenting here for the nozzle, that will be applicable for isentropic flow. Okay, and we will also make the assumption of perfect gas, because if we don't take these assumptions, then we will not be able to find the closed form solution. Okay, so now typically we have seen that in case of a nozzle, our section is something like this. So you can see that if this is the direction x, then I can say that I have some point over here where my area is minimum. So this is the point of minimum area, and from the previous lecture, if you see, I have given you the 4 different conditions, and corresponding to Mach number equal to 1, I told that dA by A is becoming 0. It means we have some minima over there. Okay, so from the physical condition we found, mathematically we had 2 situations, either there can be minima in area or maxima in area, but from the physical perspectives we found that there is minima in area. So corresponding to this, my Mach number will be equal to 1. Fine. I will be having at minimum area, I will be having nothing but a sonic situation. Okay. Now, in this sonic situation, if you see, corresponding to this, my area is say A star. Okay, so corresponding to this sonic situation, whatever area I am defining, that I am calling as A star. Corresponding to this, my velocity is V star, and as it is a sonic situation, so this V star will be equal to A star over here. Is this one clear? Now, let's say if I go at any cross section, either in the left direction of this A star or in the right direction of this A star, I will be having some different value of area. Okay, so say at any arbitrary cross section, it can be on the left or it can be on the right. Say at any arbitrary cross section, I have value of area as A, value of velocity as V, speed of sound as A, and say density as rho. So here I will be having density as rho star. Is this one clear? Now in this nozzle, what I will be having? I will be having 2 important points. One point is, this is my say exit section, which is denoted by small e, and this is my inlet section, which is denoted by I. Fine. Now, so here my area is say A exit, here area is A I. Now if you see, when I have this nozzle, at the inlet of the nozzle, what will be happening? Inlet of the nozzle is actually coming from a atmosphere, and once again atmosphere I can consider as a large reservoir. So at this point I can assume that velocity is nearly equal to 0, and then I can say that my pressures and temperatures are denoted by P0 and T0. Okay, because these are corresponding to 0 velocity, these are nothing but the our stagnant pressure and stagnant temperature. Is this one clear? Now let me once again emphasize this point, that I am saying velocity is nearly equal to 0. So please consider that velocity will not be exactly equal to 0, because if velocity is completely 0, then no flow can occur. So then fluid cannot pass into the nozzle. So there will be some velocity, but just at the entrance, all the fluid is coming from the atmosphere. So outside there will be huge area for fluid to enter. So because of that large area available just at the inlet, I can say that my fluid is coming with so small velocity that it is nearly equal to 0. Is this one clear? So if you take any pipe at the out and then you other side you take say a suction pump or suction fan which will be pulling the air. So if you take just at the inlet, so outside the inlet from multiple directions fluid will rush into the pipe. Okay, so it means that outside the fluid, inside there is a fixed area, but outside there is large amount of area from where the fluid is coming. So due to that reason, that particular fluid will be having very low velocity, and that I am assuming as nearly equal to 0. Okay, this is the reason if I have to define the ratio of AI by A star. So A star is the minimum area and AI just at the inlet or just outside the inlet, I have huge amount of area from where actually fluid is entering. Okay, so I can assume this ratio of AI by A star is something which is approaching to infinity. Then only I can give this assumption of V nearly equal to 0. Is this one clear? Okay, so AI by A star is nearly equal to infinity by considering that fluid at the inlet of the nozzle is actually coming from large area of surrounding. So I can assume this atmosphere has nothing but huge reservoir for the air. Okay, and this is the reason that I can assume velocity at the inlet nearly equal to 0 and corresponding pressure and temperature as stagnant pressure and stagnant temperature. Okay, so this is the situation. Now what is my interest? My interest is that at this throat section I already know that my situation is sonic. My interest is I want to determine what will be the variation of Mach number and properties at different points along the length. Okay, so say if I move across the length, so if I plot say Mach number versus X, then how it looks like. Corresponding to throat, where my area is A star, their Mach number will be equal to 1, and what will be the value of Mach number behind and upstream and downstream of this minimum area? What will be the value of pressure, value of temperature? So that is something which I want to actually predict over here. Okay, so now what I can do, this is one cross section at the throat and this is another arbitrary cross section I have taken. So between these two cross sections, if I apply my continuity equation, what I will be getting? I will be getting rho star A star V star equal to rho A V. Fine. And this particular V star I can replace with speed of sound at throat, so that is A star, because at this point at the throat my Mach number is equal to 1, so corresponding to this V star will be equal to A star. Is this one clear? So this I have replaced with A star, that will be equal to rho A V. Now from here if I calculate the ratio of A by A star, so A by A star will become equal to rho star by rho into A star by V. Okay, now let me multiply and divide this equation by rho naught by rho naught. Okay, on the right hand side I will multiply and divide with rho naught by rho naught. So if I do so, I can write it as rho star by rho naught into rho naught by rho into A star by V. So here what I have done, I have actually multiplied and divided with the stagnation density. Okay, rho naught. Now say this is my equation number 1. Now we know that rho naught by rho is equal to 1 plus gamma minus 1 by 2 m square whole power 1 divided by gamma minus 1. This is something which we have derived earlier, relationship in between rho naught and rho. Now, so this is your rho corresponding to any Mach number m. Now, if I calculate this particular equation, say this is equation number 2. Now, if I specifically calculate equation number 2 for Mach number equal to 1. Mach number equal to 1 is nothing but my throat. Corresponding to Mach number equal to 1, my density is rho is equal to rho star. So I can write this equation number 2 for this situation as rho naught by rho star equal to 1 plus gamma minus 1 by 2, and this m will become 1 square will be as it is, times 1 by gamma minus 1, and which ultimately will become 1 minus 1 by 2 will become 1 by 2. So gamma plus 1 by 2 whole power 1 by gamma minus 1. Is this point clear? Nothing but what I have done, I have calculated this equation number 2 specifically for the throat. Okay, so at the throat I will be having value of density equal to rho star. Is this point clear? So this I have obtained over here. So sorry, say this is my equation number 3. Now I am interested in calculating the value of A star by V. Okay, so if you see from our earlier discussion, while we have particularly talked about the normal shock waves, I have defined one Mach number m star. Okay, and m star was nothing but V by A star. Okay, so the ratio of V by A star was m star. Now if I consider the V by A star square, then it will become m star square. Okay, and m star square, if you recall in the previous lectures while we discussed about the normal shock waves, we have obtained the relationship in between m star and m, and the relationship was gamma plus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 m square. Okay, so this was the relationship between m and m star while we studied about our normal shock waves. Okay, so now from here if I take reciprocal of this, I will get A star by V whole square. So A star by V whole square will become 1 plus gamma minus 1 by 2 m square divided by gamma plus 1 by 2 m square. Say this is my equation number 4. Fine. Now what I will do, now I will take the square of equation 1. So if I take square of equation 1, what I will get? A by A star square A by A star square equal to rho star by rho naught square into rho naught by rho square into A star by V square. Fine. So say this is your equation number 5. Now if you see in the previous steps, equation number 2, 3 and 4, what I have done, I have calculated rho naught by rho star by rho naught and A star by V square. So these parameters already I have calculated. So now I can substitute all these things into equation number 5. So if I do substitute, what I will be getting? I will be getting A by A star square equal to, please tell me what is the first term? First term is rho star by rho naught. So rho star by rho naught over here is, it will be becoming 2 by gamma plus 1. Okay, because rho naught by rho star is gamma plus 1 by 2. So okay, let me write it like this only. I will make power minus 1 by gamma minus 1. Okay, so first term is gamma plus 1 by 2 power minus 1 by gamma minus 1. sorry, not minus 1, minus 2, because we have to take square also. We have to take rho star by rho naught square. So square is making 2, and because ratio is in the opposite side, so minus 2 by gamma minus 1. Is this one clear? This is one term. Then second term is rho naught by rho square. So rho naught by rho we have already calculated. So that will be becoming 1 plus gamma minus 1 by 2 m square, and this power 2 by gamma minus 1. Fine. And then I will be having ratio of a star by v square. So a star by v square is this value, 1 plus gamma minus 1 by 2 m square divided by gamma plus 1 by 2 m square. Fine. Now if you see, I have this gamma plus 1 by 2, gamma plus 1 by 2 over here, and this gamma plus 1 by 2 is having actually power. Its power will become what? One side I have minus 2 by gamma minus 1, and here I have coefficient 1. So this will be plus 1 or minus 1? Tell me. What I will get over here? So here I have 1 power minus 2 by gamma minus 1, and here I am having power 1. Okay. So this will make 2 by gamma plus 1 and whole power 2 minus gamma plus minus plus gamma minus 1. So it will be becoming gamma plus 1 by gamma minus 1. Okay. Similarly, for this, if you calculate, you will be finding it 1 plus gamma minus 1 by 2 m square, and powers will be in the same ratio. So it will be becoming gamma plus 1 by gamma minus 1, and here I was having 1 by m square in the denominator. So this 1 by m square will also come. Okay. So if you do little bit algebraic manipulations, you will find this expression. So I can write finally that a by a star square will become 1 by m square times 2 by gamma plus 1 times 1 plus gamma minus 1 by 2 m square, and this whole power is gamma plus 1 by gamma minus 1. Fine. So this is a relationship in between, A by A star. What is A? A is area at any arbitrary location, and A star is area at the throat. So if I consider that area at throat is equal to corresponding to a sonic situation, okay, and that will be the minimum area. So this A will be always larger than 1. A will be always larger than A star. So it means my A by A star ratio will always be greater than 1. Okay. So this is important to note that, because A star occurs at the minimum area point. So if A star occurs at the minimum area point, then whatever the solution we are deriving, this solution is not applicable for situation having A less than A star. So if my A is less than A star, then this is not applicable. Okay. So this situation is this solution is applicable only for the condition when my A by A star is actually greater than 1. Okay. And another important point is, over here, for a calorically perfect gas, I will be having value of gamma as known. Okay. So only unknown over here is Mach number. So it means at any arbitrary location, if I calculate the ratio of A by A star, then by just knowing that particular ratio, I can define the value of Mach number. Is this one clear? Okay. So by just arbitrarily knowing the value of A by A star at any cross section, I can define the corresponding value of the Mach number. Okay. And from this equation, you can see the nature of the equation is quadratic. Okay. So nature of the equation is quadratic. So corresponding to this, I will be finding that at any value of A by A star, I will be having two solutions of M. Okay, I will be having two values of M because things are coming in square. So when you will be taking the square root, you will be finding it will be plus minus or two roots basically. So for this type of situation, I will be finding two solutions for M. So now if I plot the variation of M as function of A by A star, then at A by A star equal to 1, say this is the situation of A by A star equal to 1. At this point, I will be having Mach number of 1. At this point, I will be having Mach number of 1. Okay. And one solution for increased value of A by A star. So A by A star less than 1 is not possible. Okay. As per the starting point of the equation. So when my A by A star is greater than 1, then I will be having two solutions. One solution will go like this, and another solution will go like this. Now if you see in this solution what you are having, here you are having Mach number less than 1. So because this is 1, this is Mach number equal to 1. So here your Mach number is less than 1. So it means this is a subsonic situation. And here Mach number is greater than 1. So here this is nothing but a supersonic situation. Now it is important to physically relate, because in case of nozzle your section will be like this. So this is your minimum area. Now on both sides our area is increasing, so I can have same value of A by A star at these 2 points. Okay, one in the upstream and another in the downstream. So corresponding to this, I will be getting a say supersonic solution of M, and at this point I will be getting a subsonic solution of M. Okay, physically is this relatable? So I can have this arbitrary value of A by A star less than 1 or greater than 1 either on the downstream or in the upstream. Okay, so I can have this situation in both the sides. So depending upon that situation, either here for the same value of A by A star, I can have Mach number less than 1 also and greater than 1 also for a convergent-divergent nozzle. Is this point clear? So from this understanding, if I know the ratio of A by A star at any point, I can calculate the value of M. Okay, so at every cross section my value of M will be known to me. Is this one clear? So here value of M will be known to me at each and every cross section. So what if I try to plot this for a nozzle? So say this is my nozzle. So this is the direction of increasing X. Now here if I plot Mach number as function of X, so I will be finding corresponding to, this is say A by A star equal to 1. Corresponding to A by A star equal to 1, my Mach number is 1. Below this my Mach number will be less than 1, and above this my Mach number will keep on increasing. So this is the variation of Mach number. So once we have defined the variation of Mach number, I can also define the variation of pressure. Okay, so say if I have to define P by P naught. say I want to plot P by P naught. What is P naught over here? The inlet pressure is P naught. Okay, so you have seen that our inlet is nearly stagnant, so inlet pressure is stagnant pressure, so inlet pressure is P naught. We know that P naught by P is equal to 1 plus gamma minus 1 by 2 m square whole power gamma by gamma minus 1. So if at any value of x I know the Mach number, I can substitute that Mach number over here and I can calculate the ratio of P by P naught. So ratio of P by P naught at the inlet will be equal to 1. Okay, because at the inlet our pressure is nothing but equal to the stagnant pressure. So at the inlet this ratio will be exactly equal to 1. So at the inlet it will be equal to 1. But when I move in the downstream from the inlet point, then what will be happening? This Mach number is actually increasing. Okay, so as Mach number is increasing, what we will be finding? I will be finding that this pressure from here will keep on decreasing. So we will get variation of pressure something like this. Okay, is this one clear? So this is how pressure varies in a nozzle. Then similarly you can plot the variation of temperature. So here you will be having x and here you will be having ratio of T by T naught. We know that T naught by T is equal to 1 plus gamma minus 1 by 2 m square. So if you plot the ratio of T naught by T, that will also look something like this. Okay. So likewise you can also plot the variation of the density. Fine. So it means that across the nozzle now, across the nozzle, if I do plot the values of the if I do know the Mach number, then I can plot the variation of all the properties. Okay, so this is very important. You can see that here Mach number is increasing, pressure is decreasing and temperature is decreasing. Important point is that we have a relationship in between A by A star and Mach number. So from that relation I can calculate the value of Mach number at any cross section, and then Mach number will be relating my variation of property with reference to the inlet properties, and inlet properties are nothing but P naught and T naught. Is this one clear? So if I have to determine the properties at any point in the nozzle, I need only two parameters. First parameter is A by A star, from which I can predict the Mach number, and then I need the inlet conditions. By just knowing these things, I can calculate actually the variation of properties. Important point is that what is the value of P by P naught at A by A star equal to 1. So corresponding to A by A star equal to 1, Mach number will be 1. I will be having sonic situation. So I can calculate for Mach number equal to 1, value of P naught by P. How much is this coming? Please calculate. 1 plus gamma minus 1 by 2 power gamma by gamma minus 1. I just want to mark over here that what is this magnitude and what is this magnitude over here. Let me know the values. 0.528.
Sorry, didn't mean to disturb. You can carry on. I just wanted to look at the room for program.
Okay. And what about T by T naught? T by T naught is 0.83. 0 point. So it means that corresponding to A by A star equal to 1, I will be having the ratio of P by P naught as 0.528 and ratio of T by T naught as 0.833. Okay, so is this point clear? Now it is important to understand that, so till now what we have done, we have some inlet pressure and corresponding to exit area we are finding some exit pressure also. Okay, now we know that if I have to achieve the flow through a nozzle, okay, what I have to do? I have to create some pressure difference between the inlet and the exit. If you just take a nozzle and place it in the atmosphere, will it allow the flow to happen? Consider you have a nozzle, you have placed it in the room. So will the flow will take place from left to right, or say from convergent to divergent section? Flow will not happen. So for the flow to occur, what we have to do? We have to create the necessary pressure difference across the nozzle. Because unless or until we are providing the pressure difference across the nozzle, then actually we will not be able to achieve the flow. Okay. So it means that this should be the ideal pressure difference across a nozzle in order to achieve Mach number of 1 at the throat. Is this one clear? So I am getting over here some value of exit pressure. Okay, corresponding to this is my exit, and corresponding to this I have some value of pressure. So here I will be having P exit by P naught. Okay, so this P exit by P naught ultimately what is happening, this P exit by P naught, actually this particular value has to be maintained at the exit point, then only I will be having the sufficient pressure drop across the nozzle to create a situation when I can get a Mach number of equal to 1 at the throat. Okay, if my pressure is other than this pressure ratio, then actually I can have some situation when Mach number is not reaching to the sonic situation at the throat. Is this point clear? So pressure difference across the nozzle has to be controlled properly in order to make it work as a isentropic expander for changing the situation for from subsonic to supersonic flow situation. Okay, if I deviate from this, then what will be happening? That is the question. If I deviate from this, it is for sure that I will not be able to achieve a Mach number of 1 at the throat. But what will happen? Okay, so to understand this, let's now talk about the effect of pressure. So what I am saying is that, say PE is the pressure which was required to, I am calling this as PE. So PE is the pressure which is required to maintain Mach number equal to 1 at the throat, or I can say at A by A star equal to 1. Okay, this is the pressure PE. But if my pressure difference between starting and exit is not equal to PE and it is other than PE, then what will be happening? That is something which I want to actually determine. Okay, so let's consider that once again the similar nozzle I am having, and I need to plot, say, variation of Mach number as function of x. Similarly, I need to plot variation of pressure as function of x, or I can call it as, say, P by P naught. Okay, now this is the minimum area, so this is the point where my A by A star is equal to 1. Okay, say this is my inlet pressure, so inlet P by P naught will be 1. Okay, and say this is the pressure at the exit corresponding to PE. Understood? PE means the pressure which is required to maintain Mach number equal to 1 at the throat. Okay. Now say if I consider that I have, in place of choosing PE, I have chosen very small pressure difference across the inlet and outlet. So I have this PE1 by P0 over here, and this PE1 is selected in such a way so that P by P0 at the inlet and outlet are actually very, very small. So what I have done, I have chosen a very, very small pressure difference. Okay, so if I choose a very small pressure difference, then what will be happening? I will be having some flow in the nozzle, but flow velocity will be very, very low. So from Mach equal to 0, my flow has started, but flow rate was so small that I am not able to reach corresponding to the Mach number of 1. I am reaching to a Mach number which is very less than 1 at the throat. If my Mach number is less than 1 at the throat, then further downstream I am having an increased area. So this is becoming a subsonic situation. So I will be having further decrease in the Mach number. Is this one clear? For this type of situation, what I will be finding? I will be finding that I will be having some pressure drop, something like this, because here Mach number was increasing, but then Mach number started decreasing. So as it started decreasing, here I will be having once again the regain of pressure, because now this section is acting as a diffuser. So here once again I am having gain of pressure. Is this one clear? Then, so this is my curve corresponding to first situation when I have ratio as PE1 by P0. Now if I take another value is say PE2 by P0. So in case of PE2 by P0, what will happen? I will start at this point, but now I have slightly larger pressure drop. So for slightly larger pressure drop, my Mach number point will be slightly shifting up. This is corresponding to PE2 by P0, and here I will be having here larger pressure drop, and once again the regain up to this point. Fine. Then third situation, PE3. So say this is PE3 by P0. Okay, and then the final one, when I will be just able to make Mach number equal to 1. So corresponding to that, this will be my required pressure drop, and my Mach number will reach to exactly equal to 1, and then something like this. Fine. So it means that for different values of pressure difference across the nozzle, I can have different variations of the Mach number, and all these situations, for all these situations, Mach number is less than equal to 1. So it means that in case of subsonic situation, I have the presence of infinite number of isentropic flow situations depending upon the pressure drop across the nozzle. Is this one clear, what I am saying? So what I am saying is, if you change this pressure drop across the nozzle, then you will be able to achieve different isentropic situations. Okay, and for all these situations our Mach number is less than equal to 1. So it means that for Mach number less than equal to 1, particularly for subsonic situation, if we control the pressure drop, then I will be having large infinite number of solutions possible for this equation whatever I have just derived in the previous section. Okay. However, for supersonic flow situation, if we go, we will be finding that for supersonic flow situation we will be only having a unique solution. Okay, so how that unique solution will come, why for supersonic flow situation we are not having multiple solutions, that is something which I will actually discuss in the next lecture. Okay, so now I will stop at this point and we will have further discussion in the next lecture.